That's the correct link. My apologies. Okay. Let's see. Where's my slideshow? I guess right here. Okay. Have you guys ever seen Mythbusters? No? Anybody seen Mythbusters? Anybody want to put their phone away? Have you seen Mythbusters? Man, that show is good. That's a good like background show, you know?
It is a friendly version of that one show, mainly for adults. Because like they do stunts with anything.
Oh, like Jackass?
Yeah.
Yeah, it's kind of like, it's a little more scientific than that.
Oh, very friendly, but more educational version.
Yeah, definitely more educational. Jackass is,
Fun.
yeah, that's a,
Of, like, that for this reason.
yeah. Yeah, there's a lot to unpack with that one. Anyway, this is a picture. I don't remember, I think this guy's name's Adam? This guy's name Jamie? I don't know, but apparently they are the name of that other show. At least Jamie is apparently. He's not a super nice person apparently. And they also hated each other. Anyway, that's a good show to watch if you get bored. Okay, so we're going to be talking about PowerPoints that don't work. Whoop, whoop. Come on, man. There we go. Okay, we're going to be talking about Newton's laws of motion. So there are 3. We're going over the first 2. So Sir Isaac Newton was an Englishman. Well, was he an Englishman? Yeah. Englishman, and he lived from 1642 to 1727. He was a physicist, mathematician, astronomer, philosopher, and theologian. So he dabbled in a lot, clearly. Yeah, that's a lot of jobs. But back then, you know, if you think about it, like all this stuff was discovered a long time ago. Most things were discovered a long time ago. It takes a lot more to find new things these days because we've done so much so far, right? So you have to kind of devote your whole life to one field at this point, but in the 17th century, not so much. So he discovered the laws of gravity. So he's the guy that the story of like he was sitting by a tree and an apple fell from the tree and hit him on the head. I think it actually just fell on the ground, but that sparked the idea in him that there is some force pulling things towards the ground. The laws of motion, and he created calculus. But I'm pretty sure that's whitewash history. Pretty sure calculus was created in Asia or Africa. I can't remember exactly, but yeah. So quote unquote creating calculus. I'll get back to you on that one. So if you have to take calculus, you can blame him. Let's just blame him. Okay, so first law, the law of inertia. Okay, so when we're looking at Newton's laws, you're going to want to remember what the law is about and be able to apply it. So this law specifically, we're going to learn about free body diagrams, kind of, and then be able to apply that to an object. And it kind of ties in with the second law as well, which is why we're learning them together. Okay, so the law of inertia. An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an unbalanced force. So the tendency, inertia, is the tendency of an object to keep doing what it's doing. So there's a Chromebook sitting right here on the desk. It's going to continue to sit on that desk until I pick it up and chuck it across the room. Then I put an unbalanced force upon the object, and so I created an acceleration. So basically things want to keep doing what they're doing. So, you go home from school, or you're already home at school, and you decide to, turn on some Netflix. What are we watching these days? Bridget? No, I'm not going to even say it. What are y'all watching these days? Anything good? Oh, okay. Yeah, that's what I'm saying. What are you watching on Netflix? Anything? All right, whatever's in the top 10 of Netflix, we're sitting down, we're turning it on. Rick and Morty, when's season 3 or season 4? How many seasons are we? 5? Has the new season come out? Should be soon. I don't know. I just see it when it shows up. Okay, so you're sitting down. You decide to watch Rick and Morty. Of course, you're also scrolling on Instagram on your phone, right? If inertia is acting upon you, you're going to keep doing that. You're at rest, so you're going to stay at rest until you see that you have. Oh yeah, maybe you run out of season, and so you're like, dang, I've been sitting here for 5 hours. Maybe I should get up and do something. Or you get a notification from Google Classroom that you have an IPC test to study for, right? That would be kind of an unbalanced force. I mean, that's a little more conceptual, but so some sort of unbalanced force to get you up off the couch. Or maybe somebody kicks you, I don't know. So that is inertia. Things wanting to do, they either want to stay at rest or they want to stay in motion. So, tablecloth trick. So the magician's trick where they pull the tablecloth out and all the place setting stays on the table? I've never seen it in real life, but I see it on TV all the time, and usually they're not good at it. So the dishes have an inertia to stay in place because they're already at rest. Gravity is pulling them down on the table, and they want to stay that way. So if you are fast enough at pulling the tablecloth out from underneath them, they will continue to stay at rest because the force of friction you are creating isn't enough to unbalance the force of gravity. Okay, so let's see, we're going to talk about friction in a second. Okay, So cars are a really good, like, real life example of inertia that you guys have experienced. So, you know, when somebody, for some reason it happens more in the passenger seat, because I think when you're the driver, you're like more tense and you're kind of more in the center of the car. But when you're in the passenger seat and somebody takes a turn, you know that feeling of like getting pulled in with the turn? That is inertia. So you're going straight and your body is going straight and it wants to keep going straight, but the car turns. And so your body's kind of feeling the force of wanting to still be pulled straight. That is inertia. So similar to if you get into a head-on car collision, the car is stopping suddenly. The wall or whatever you hit is making an unbalanced force against the front of your car. But the passengers continue to move forward because of inertia. So you get jerked forward because your body wants to keep moving. So seatbelts are designed to help with that, and airbags, because they're kind of making you part of the car. So when an unbalanced force acts upon the car, you will also stop with the car. Of course, you still get jerked forward a little bit. Obviously, the seatbelt isn't like keeping you pasted into the seat, but it's better than, you know, when the Ford Model T was first made and they didn't have seatbelts and they didn't have speed limits and they just drove super fast all around on really crappy roads. And if they hit something, they would literally fly out of their vehicle. Also, I don't think they had windshields for a while. So there was really nothing to stop you. Full force, going whatever speed you were going, you would just keep going that speed until you hit the ground. So yeah, similar to why it's super dangerous to be on a motorcycle. If you hit something, your body will keep going and then you're on the pavement. So, yeah, you go flying. So same used to be with cars before we had seatbelts. Yeah. So if you're ever on a motorcycle, please be super safe, wear protective gear, wear a helmet, save your noggin. But yeah, so that's why we have seatbelts. And little fun fact, I don't remember what car company it was, but they decided to patent the seatbelt and give it away for free so that all cars could have seatbelts and save a bunch of lives. I don't remember who it was. Now the fun fact is not as fun. I know. I'm not good with I'm only good with remembering half facts. So that's why I'm terrible at trivia. I still like to go, but it's always like a tip of my tongue sort of thing. Okay, so I'm getting really distracted today. It's the ADD. Okay, so here is a question you can answer on Pear Deck. Please do. So describe how this scene exemplifies Newton's first law of inertia. Inertia. I've only got 16 people on the Pear Deck, and I need way more than that. Is that you? Is that you or is that you? Let's see. Who invented the seatbelt? Dun-dun-dun. Volvo. Niels Bohlin invented the 3-point seatbelt. Okay. Where was calculus invented? Mhm. Oh my God. Wow. Isaac Newton was an interesting person. All right. So calculus was developed in the 17th century by Isaac Newton and Gottfried Wilhelm Leibniz, independently of each other, but they published around the same time. But elements of it appeared in ancient Greece, then in China and the Middle East, and then still later in medieval Europe and India. Okay. All right, so everybody pretty much got it. Oop. So this was an example of Newton's first law of inertia because the bike had an unbalanced force act upon it, being the wall of tires, right? But the guy is not attached to the bike, so his body wanted to keep moving forward no matter how fast he was going on his little dirt bike. And so he keeps going until the force of gravity and air friction really kind of stops him. So the force of gravity, and then he hits the ground at some point. So good. Okay, so unbalanced forces. Gravity. So if you guys remember the test question about the apple falling, and the acceleration that we used was the force of gravity. The force of gravity on Earth is always the same. It is 9.8 meters per second squared. So this is the force, I need a bouncy ball, that causes things to fall from the sky. What's pulling it down? Gravity at an acceleration of 9.8 meters per second squared. Friction. Friction is the force acting upon things that are on a surface or in the air. So when I kick this, it's not going to roll on forever. Well, it's not a perfect object for one, but the surface that it's rolling on, even though it's quite, it's like smooth and shiny, and there's like not that much friction compared to like if it was rolling on grass. Yes, that's a good example. Grass would have quite a bit of friction. So the force of friction will slow something down. And it's always going to be reacting in the opposite direction of the force that is pushing it forward. Okay, so we're going to learn about free body diagrams, and we'll be drawing our vectors of force. So if I was pushing this apple down the floor, I would be pushing it this direction with an unbalanced force, which we're going to learn the equation. And then friction will always be acting in the opposite direction, trying to slow it down. But of course, it's not enough to push it back towards me. It's just going to be enough to slow down the acceleration. A lot of the problems we're going to be doing will probably not include friction. So when we're doing practice problems in physics, you'll see there's a lot of, how do we say? I guess special circumstances. So when a lot of times when we're calculating like the force of gravity, or like the mass of something that I'm dropping, we're not going to be including air friction in that calculation, or when I'm pushing an object across the room, we're probably not going to count surface friction unless we're told to. it will say. So there will be a lot of extra information and questions saying like in an ideal situation with no friction or, you know, whatever. So surface friction is going the opposite direction from an object that's sliding. Air friction is going in opposite direction from an object that is falling. So it's pushing upward. You're hitting particles of air as you move downward, and it is pushing with a force that is upward. So it is slowing you, not very much. But so that's kind of the reason why things seem to drop at a different rate. So technically the force of gravity is the same, or the acceleration of gravity is the same. So they're moving at the same acceleration, but the force of air friction that's pushing it back up is going to be different depending on the surface area. So this, if this was an actual apple, would fall faster than a piece of paper because the piece of paper has more of a force of air friction acting upon it in the opposite direction. So it's going to fall slower. Okay, so we're going to talk about mass and weight again. So remember, weight is your mass affected by gravity. So just keep that in mind moving forward, and I'll go into it more in a second. Okay, so masses always have a gravitational force of attraction between them. So when you're standing next to your friend, you and your friend have a gravitational attraction towards each other, but you will always lose this tug of war with planets because obviously they're more massive. Earth keeps us grounded because it's so big that it has a gravitational pull that keeps everything down. But then the larger of a mass, the larger of a planet you have, the more of a gravitational pull you will have. And then the smaller of a planet compared to Earth, the smaller the gravitational pull will be. So if you weighed yourself on Mars, you will weigh less than you would on Earth. A third less, because the force of gravity is about a third of the force of gravity on Earth. So weight is basically the measurement of force that gravity is having on a mass. So weight is mass times gravity, or mass times acceleration. However, remember that your mass does not change. So you are still all of you. You have all of your molecules, right? When you go to Mars, ideally you don't lose any parts. So you still have the same mass. Mass will never change. But your weight is actually the measurement of the force of the planet that you're on pulling your mass downwards. So the weight will change, but your gravity will not, or your mass will not, sorry. Okay? So here's a question for you. Jupiter is about 318 times as massive as Earth. If Jupiter had a surface to stand on, it's a gas planet, so it doesn't, but in this situation, it has a surface to stand on, and you brought a scale with you to Jupiter, would you weigh more or less than you weigh here on Earth? How would your mass change? This is slide 9. This mask is really making it hard to breathe today. Okay, so remember, sorry, the bigger the planet is, the more gravity it has. And I'm asking about how much would you weigh? It should show your answer when you're on the slide. I can see your answer. Colin, what does that mean? Does that mean I was too busy on TikTok to listen to what you were saying? Okay, just a reminder for those of you who are not answering, I do grade your participation. So at least give it a half-assed try. Okay, so yes. Yes, I can see your response. Okay, so Jupiter is about 318 times as massive as Earth. So the gravity of Jupiter is almost 3 times as much as Earth. So if I went to Jupiter, even if I couldn't stand, the force of gravity pulling on me would have me weighing almost 400 pounds. About 3 times that of Earth, because Earth's gravity is 9.8, Jupiter's gravity is almost 25. So, your mass would be the same, because you're taking, let's say I'm here now, and then in, a couple seconds, I'm on Jupiter. No time passed, just doing a hypothetical, right? So my mass isn't changing. The amount of, molecules that I have are staying the same. It's just the gravity that is affecting me that is changing. So, think about it like this. So, I don't know how many of you like know too much about the solar system, but generally the bigger planets have a lot more moons. It takes it takes a great gravitational pull to have a moon. We have one because we're like decent sized, right? I'm pretty sure Mars doesn't have a moon. Too small. Jupiter, however, has 12? I'm not a professional. I don't know. I'm not 100% sure. Really? I'm doing a lot of Googling today. Uh, uh. 23. When 3 of Jupiter's moons are shown. Wait. Okay, it has inner and outer moons, I guess. So it has 79 satellites, 3 that are officially, I think, classified as moons, and then I guess 76 that are not considered moons because they have to be a certain size. But either way, to pull something into your, I know if we had 3 moons, that would be crazy. To pull something into your gravitational orbit requires a great amount of gravity and mass. So usually as you get bigger, your gravitational pull will be more. It also changes time in a weird way, which I will not explain to you because I don't 100% understand it. So, second law, okay? So first law was inertia. Second law has to do with force, mass, and acceleration. So the acceleration of an object is dependent on its mass and the net force that is acting on it. So Newton's second law means that applying a larger net force or reducing an object's mass will both result in a larger acceleration. So think about if you decrease the mass of something, if you make it lighter, it will be easier to move. Also, if you apply more of a force on it, it's going to move faster than if you applied less of a force on it. Like if you just touch it with your finger, depending on the object, it might still have an acceleration, but if you picked it up and threw it, it would have more of an acceleration. All right. So next conceptual question on slide 11. Second law, why is it so easy to throw a baseball and yet so hard to move a stalled car? Okay, so the reason why we learn both of these laws together is because inertia and the second law, force, mass, and acceleration law, kind of play hand in hand. So remember, an object's not going to move unless there's an unbalanced force acting upon it. So you have to, basically, in both of these cases, beat the force of gravity in order to move the object. Well, it's a lot easier to create an acceleration with a lighter object than it is with a heavier object. So the smaller the mass, the easier it is to create that unbalanced force and get that object moving. So baseball, a lot smaller mass. You could be putting the same force into the throw that you would be into pushing the car, but since the car is so much heavier, it's going to be more difficult to make that unbalanced force to push the car forward. Force equals mass times acceleration. Okay, so these are our new equations that we're going to be looking at. So acceleration, well, let me start with force equals mass times acceleration. That's probably the easiest one to remember. F equals ma, just kind of rolls off the tongue a little bit easier. So similarly to how we can rearrange the speed equation to find distance or time, depending on what we were looking for last unit, right? Which some of you had a little bit of trouble with, but that's okay. We'll get used to it. So you can rearrange the force equation to get acceleration equals net force divided by mass. Okay, so how do we get that? Well, if you're looking for acceleration by itself, you have to divide by the mass on both sides. Since it's multiplied by this acceleration right here, you would divide by mass on both sides to rearrange that equation. So hopefully you guys have gotten used to doing that if you don't have the already rearranged equations memorized. So F equals ma. So that's our third acceleration equation that we have now. So we had our first one, which was change in velocity over time. Our second one, which was change in velocity over distance. And now we have change in force over mass. All right, this is your problem, and this is the last slide we have for today. So, a large box accelerated at a rate of 5 meters per second, or meters per second squared. The mass of the box is 35 kilograms. How much force was used? Oh, so may all need to go back and look at the other slide. Reread the question. Okay. Let me show you. So I'm going to start by writing out my equation, right? Force equals mass times acceleration. That is hard to see. What would be cool? Okay, so now I'll write it over here. Force equals mass times acceleration. Okay, so now go through your problem and look and see what you're looking at and what you're looking for. Okay, a large box accelerated at a rate of 5 meters per second squared. So I know my acceleration is 5 meters per second squared. Oh, leave me alone. Okay, the mass of the box is 35 kilograms. So my mass, sorry about my handwriting. Okay, and then how much force was used? So I know I'm looking for force, which is a big capital F. Okay, so I know my equation already. It's force equals mass times acceleration. So I just have to plug in 35 kilograms times 5 meters per second squared. So what was it? 175, right? 175 newtons. So remember when I said, I know I mentioned in a practice problem like maybe once. So when you're doing directions, you want to put them in brackets like this, because otherwise, now that we're doing newtons, it's newtons. So capital N stands for newtons. A newton is 1 kilogram times meters per second squared. So if you guys remember your units, you don't really have to remember equations, or vice versa. If you remember equations, you don't have to worry so much about units. I mean, you still have to write them down, obviously, but you don't have to be worried about it. But like, so if I know newtons is, let me see, let me clear all this. So 1 newton is 1 kilogram times meters per second squared. So I know these are my units. So I know if I'm going to be getting to newtons, which is the unit for force, if I'm looking for force, I know I have to multiply a weight by an acceleration. Okay. All right, what questions do you guys have? Anybody? All right, somebody tell me Newton's first law. Colin? Newton's first law? You'd hear it? Newton's first law? Anybody? Yes, Cody got it. Things at motion stay in motion. Objects at rest want to stay at rest. The law of inertia. Okay. And the second one is basically the equation F equals ma. Force equals mass times acceleration. Okay. Guess I can sit down now. So, okay. So, if you, let's see.